Button to okay. 20.3 force on moving charge. That's the syllabus. Right, page 162. Right, summarize for you what we will be studying. Okay, you can use your textbook. Okay, 20.7 charge particle. Right, we are, we are using another method for measuring the right, charge particle can be electron. Millikan's experiment, evidence of quantization of charge, diffraction of charged particle in electric and magnetic field, velocity selector using E and V field. Okay, magnetic force on moving charge. There's your B going in, and there's your charge, positive charge, moving to the right. So the force is perpendicular, BQV, right? B is a perpendicular component, where B is a component of B perpendicular velocity. So in this case, it's perpendicular velocity, can put V, right? Force on charged particle, see whether you can get it outwards or not. Using Leibniz rule, that's all. Current is the movement of positive charge. Can
Yeah, we are.
field going in, current is going to the right.
Yeah, I can get it.
Can okay. And if it's at an angle, instead of coming out, it's going at an angle to the field. Right? Remember, the field is perpendicular, BQB. That's a perpendicular component, V sine theta. So V sine theta is a perpendicular component. Force is maximum when the magnetic field is perpendicular to the velocity of the charge and magnetic flux density. Right? You're required to remember and use it. Right? There's a vector equation which you study when you go to university. Right? That's a cross product. Where's the direction of the force? That's a charge moving there. That direction of. So where's the direction of the force?
Mm, Up. Is it up?
Okay, let's see. That is your B component of B perpendicular to the current or charge, moving charge. Out of page. Okay,
Okay.
you got it right.
I said up.
Oh, you say up. Oh, then you got it wrong.
Wait, what's the difference? Wait, why is it out of page?
There's already got one direction already. Up or down is taken already by
Uh,
the charge. Then left or right is taken by B already. So it has to be out or in. No?
oh, okay.
Right? You can alternatively think of V as perpendicular to the field. Right? Means that's the action of the current. And BQ V sine theta. Right? That's out of the page again. Same thing. Okay. Moving charge particle perpendicular to the magnetic field. Force does not change the speed of the particle as is always perpendicular to the velocity. Change, right? Change direction of velocity, that's all. Force is constant in magnitude. Is it circular or parabolic path? Right? That's the first topic we learned. Circular or parabolic path?
Circular.
Circular. Right? Charge moving perpendicular to the field. Direction of force is using flaming through into the page. So in this case, centripetal force equals magnetic force. So as the magnetic force provides the centripetal force. Okay, magnetic force provides the centripetal force. Direction gap for Fleming's second rule. Right? A charged particle moving in a plane perpendicular to the magnetic field. Right? That's the diagram there. Into the page, magnetic field is going to the page. It will move in circular path with magnetic force playing a role of centripetal force. Direction of the force is given by, well, you can try that, and you can show you that the magnetic force is going towards the center there. Equating the centripetal force with the magnetic force and solving for R. The magnetic force, the centripetal force, V and V cancel off. Okay? So you want your R cross multiply BQ, take it down. Okay or not? Any comment?
Yeah.
Right? No need to memorize that, but if you want to memorize, you can think of momentum sitting on B, and the B is you can cancel one B, right? MVQ, BQ. Radius of scalar path depends on momentum of the particle. B, magnetic flux density, and charge. Or it depends on specific charge, mass divided by charge, right? And the velocity. Diffraction of positive and negative charge in a magnetic field. Check direction of diffraction using Fleming's left-hand rule, whether it's correct or not. This is for positive charge, negative charge. Negative charge, you just think of the current as moving opposite direction. For motion of electrons, determine the force on conventional current opposite direction to the current flow. Can?
Yeah.
Right? Deflection of radiation, gamma ray will pass through. Beta, smaller mass, slower velocity, larger velocity. Beta, two positive charge, greater mass, less deflection. Field is out of the page. Right? You can check, see whether you can get the direction or not. Can? Alpha field is coming out of the page. Current
I
is
don't
going
understand what's out of page actually, teacher.
out of the page, coming towards you.
Oh, miss the force coming towards you.
No, the field is towards you.
Oh, the yeah, yeah, yeah.
Field is towards you. Field is towards you. Then alpha is the direction of a current. No? So the force should be downwards. So,
Yeah.
right? That's the application. Right? Radius depend on mass to charge ratio. Right? Phi method can be used to show variation of attractive force with applied voltage. How the attractive force changes with separation between charge conducting plates. Setup is necessary as the force measure is very small. We need a top end balancer because the force is very small. Let's set up current balance to measure the attractive force between the plate, parallel plate capacitor. Set up the apparatus as in the diagram, with polythene spacer between the parallel conducting plate. When the power is off, note the mass of the balancer. Right? You just measure the capacitor. Turn on the power supply and note the less attractive force now, the new mass. So you don't have to worry how not to know how to calculate the force as well. The force is the change in mass times G. Delta M is change in mass times G. Beam of charged particle. Charged particle can be electron, proton, alpha particle, or ions. Charged particles are emitted with different speed. Can we isolate the charged particle with a particular speed? By isolating a charged particle with a particular speed, then we can measure the specific charge. And specific charge is the charge to mass ratio. This allows us to identify the charged particle. Right? You can find the mass of the particle. Okay, we come to velocity selector. Velocity selector, charged particle in electric and magnetic field. What's the velocity selector? Velocity selector allows charged particle with a particular speed to be selected from those entering with different speed. Right? You see the electron coming in will be at different speed. Those with different speed will be deflected away from the straight line. Only a particular speed will go straight through. Requirement. Electric and magnetic field at right angle to one another, causing deflection in opposite direction. That's the requirement. Charged particle enters the field with velocity normal to the two field. No deviation. You got 10 more minutes. No deviation, no deflection for particles with selected velocity where the magnetic force equals electric force. Okay, deflection in electric field. Beam of electron will be deflected outwards. So negative charge particles are deflected outwards in electric field. Positive charge are deflected in different direction. Going deflection downwards. So if it's positively charged, basically the positive plate will attract the electron. Negative plate will attract a positive charge. If charge is Q, electric field strength is E, then the force is electric force is EQ. Deflection in magnetic field. For charged particle Q moving with velocity V perpendicular to magnetic field or strength V, the particle is deflected both perpendicular to B and V. Okay, can you given you the formula?
Yeah.
Magnetic force BQV, electron is deflected downwards. Okay, make sure you can get the direction. The force is that way. With no field, without any field, the electron will move horizontally. Okay, charge moving in magnetic field. When magnetic field is applied, the electron is deflected downwards with a force BQV. Can get the direction? Field is going in.
Yes.
Okay. With electric field, the electron will be repelled by negative charge or attracted positive plate. So the action of the electric force. So we both together on. Right? There's the magnetic force, there's the electric force. For no deflection, that means electron move straight through. The magnetic force balance the electric force. For equilibrium, magnetic force equals electric force. Q and Q cancel off. So we got V is EB. The formula is independent of mass and charge of the particle. We need to adjust electric field and magnetic field to choose a particular particle with a particular speed. That's what the formula is telling you. What happens if it's a positive charge of the same velocity? Same thing, it's just deflected in opposite direction. Two forces reverse in direction, still balance. Right? Same formula can be used. Electric force is upwards, electric force is downwards. It's still equilibrium. So we say same formula. What happened for electron of different speed? For equilibrium, is that right? Magnetic force equals to electric force. For electron of greater speed than VE, this is different really. This is greater, magnetic force is greater than their electric force. So it's deflected downwards. For slow electron, right? Magnetic force is smaller than electric force. So it's deflected upwards. So. Okay.
Yeah.
Specific charge is charge to mass ratio. By knowing the charge of the electron by Millikan's experiment, we can determine the mass of the electron when the specific charge is known. Right? E over m can be known. E is known, then mass can be known. Right? There's a mass spectrometer. You don't need to know. There's your ion source. There's a velocity selector. The ion separation. Okay, you won't bother about that. You are only interested in velocity selector. Right? Radius can be measured from here, from the diameter. There's an alternative apparatus. You won't bother also. Lah. Right? From the electron emitted by the cathode and then accelerated by the anode. Right? That's the formula. EV is half mv squared. Then you can get our equation from this equation, E over m. Get that? Electron move velocity v as we reach velocity selector. Then E of v replacing that v. As I say, this is just for info only lah. No need to worry about it unnecessarily. That's how we calculate the specific charge. Okay, any question? If not, we'll go to hall voltage. You will be cut off halfway lah. Understand the origin of the hall voltage, derive and use. Okay. Hall effect. This is the thickness. This is the length. Length is the same direction as the current. There's a current flowing in. That's the width. Width is where when a conductor or semiconductor, right? This one can be a conductor or semiconductor, is placed in a magnetic field in such a way that magnetic flux density and current are at right angle. Okay, current going in, magnetic field coming down at right angle. There's a B coming down. There's a current going in. There's a current. Potential difference is observed across a conductor. This is known as Hall effect. The PD across the conductor is called the Hall voltage. Right? That's how we measure across this one surface current, this surface magnetic field. So the perpendicular surface, we measure the whole voltage. Right? That's how it looks like. That's the conductor. This is usually semiconductor. This apparatus measuring. Right? Called Hall probe. Mechanism of conduction. Right? This is your AS work. Q is the charge particle. N is the number of charge per unit volume. A is the cross-sectional area. V is the mean drift velocity. Right? Just review. Derivation of the equation. They won't ask you already. They just require you to remember the formula. You can get it from a formula sheet, I think. Okay. This is a surface. This is a surface to measure B. That is a surface. That's the direction of current. Current is the length. And that is where the whole voltage should be. Right? K is a constant. K is 1 over NQT. D is the thickness. B is the magnetic flux density. I is the current. All effect can be used to measure magnetic field with Paul probe. Okay, it will be cut off anytime. So you want a class on Thursday?
Yeah.
Not sure yet. I have to confirm with you.
Okay.
Right? That's a even in a data sheet, you need to know how to derive. NQT is a constant of conductor. A slice is thin. Right? That's the thickness. Small t, when the whole voltage is large,